Hello there, and welcome. Tonight, we're going to drift through one of the universe's most mysterious and invisible forces. Gravity. That gentle pull beneath your feet. That cosmic architect shaping galaxies and bending light itself. As you settle in, allow your breathing to slow. Let your thoughts quiet, and prepare to explore 100 fascinating truths about the force that holds everything together, from the smallest atom to the grandest cluster of stars stretching across the void. Let's begin. Gravity is one of the 4 fundamental forces that govern our universe. Alongside electromagnetism, the strong nuclear force, and the weak nuclear force, gravity shapes the behavior of everything from subatomic particles to entire galactic clusters. These 4 forces are the invisible threads that weave together all physical interactions we observe. While the other 3 forces can be described through quantum mechanics and the exchange of special particles, gravity stands apart, unique and mysterious, operating on principles that continue to challenge our understanding of reality itself. It is by far the weakest of the fundamental forces. In a demonstration of just how feeble gravity truly is, a simple refrigerator magnet can overcome the gravitational pull of the entire Earth when it lifts a paperclip. The electromagnetic force binding that magnet's atoms is vastly more powerful than all of Earth's mass pulling downward. Physicists have calculated that gravity is roughly 10 to the 40th power times weaker than electromagnetism. That's the number 1 followed by 40 zeros. To put it another way, gravity is a trillion times weaker than the electric force. This profound weakness makes it incredibly difficult to study at small scales, yet on cosmic scales, where electromagnetic forces cancel out, gravity reigns supreme. Despite being the weakest force, gravity has an infinite range. While the strong and weak nuclear forces operate only within the impossibly small confines of an atomic nucleus, gravity extends outward forever, diminishing with distance but never completely vanishing. This infinite reach means that every particle in the universe, no matter how distant, exerts some gravitational pull on every other particle. The force weakens according to the inverse square law, meaning that if you double the distance between 2 objects, the gravitational force between them becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. But no matter how far you travel, gravity never quite reaches 0. It fades like the light of a distant star, growing dimmer and dimmer, but always present, always pulling. Gravity always attracts and never repels. Unlike the electromagnetic force, which can both pull charged particles together and push them apart depending on their charges, gravity knows only one direction: inward. Every mass attracts every other mass. There is no such thing as negative mass to create a repulsive gravitational force. This one-way nature of gravity is what allows it to dominate the structure of the universe on large scales. While positive and negative electric charges tend to balance out in large objects, leaving them electrically neutral. There is no cancellation for gravity. Every atom adds its pull to the total, creating the immense gravitational fields of planets, stars, and galaxies that shape the cosmos we see. Isaac Newton first described gravity mathematically in 1687. In his revolutionary work, Philosophiae Naturalis Principia Mathematica, Newton presented his law of universal gravitation. He showed that the same force that makes an apple fall from a tree also keeps the moon in orbit around Earth and the planets circling the sun. Newton's equation states that the gravitational force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. This elegant mathematical relationship united the heavens and the earth under a single principle, transforming our understanding of the cosmos. For more than 2 centuries, Newton's law stood as one of the most successful theories ever created, accurately predicting the motion of celestial bodies and guiding our exploration of the solar system. Albert Einstein revolutionized our understanding of gravity in 1915. With his general theory of relativity, Einstein showed that gravity is not actually a force in the traditional sense, but rather a consequence of the curvature of space-time itself. According to Einstein, massive objects like stars and planets warp the fabric of space and time around them, much like a heavy ball placed on a stretched rubber sheet creates a depression. Other objects moving nearby follow the curves in this warped space-time, giving the appearance of being attracted by a force. This geometric interpretation of gravity was radical and profound. It revealed that space and time are not separate, fixed backgrounds against which events occur, but are themselves dynamic and responsive to the presence of matter and energy. As physicist John Wheeler eloquently summarized, matter tells space-time how to curve, and curved space-time tells matter how to move. The theory of general relativity has passed every experimental test, from the precise precession of Mercury's orbit to the bending of starlight around the sun, from the slowing of time in gravitational fields to the recent detection of gravitational waves. Einstein's theory has proven remarkably accurate. When astronomers observed a solar eclipse in 1919, they confirmed that starlight passing near the sun was deflected by exactly the amount Einstein predicted, making him an international celebrity overnight. Modern tests using atomic clocks, spacecraft navigation, and observations of distant pulsars continue to verify general relativity with astonishing precision. Even the GPS satellites in orbit must account for relativistic effects, both from their motion and from being in a weaker gravitational field than Earth's surface. Without these corrections, your navigation system would accumulate errors of about 10 kilometers per day. Gravity curves the path of light. Though light has no mass, it does possess energy, and according to Einstein's equivalence between mass and energy, anything with energy responds to the curvature of space-time. When light from a distant star passes close to a massive object like the sun, it follows the curved geometry of space, bending from what would otherwise be a straight path. This gravitational lensing effect has become a powerful tool in astronomy. When light from extremely distant galaxies passes through massive galaxy clusters between them and Earth, the intervening gravity acts like a cosmic magnifying glass, distorting and amplifying the light. Sometimes this creates multiple images of the same distant object, or stretches it into beautiful arcs and rings. Through this natural lens, astronomers can study galaxies that would otherwise be too faint to observe, peering deeper into space and further back in time. Gravity slows down time itself. One of the strangest predictions of general relativity is that time flows at different rates depending on the strength of the gravitational field. The stronger the gravity, the slower time passes relative to a region with weaker gravity. This isn't an illusion or a trick of measurement. Time genuinely runs more slowly near massive objects. An atomic clock on Earth's surface ticks slightly slower than an identical clock aboard a satellite in orbit. The difference is tiny but measurable, and must be accounted for in technologies like GPS. If you were to hover near the event horizon of a black hole where gravity is immensely strong, time would slow dramatically. To someone watching from a safe distance, you would appear to move in slow motion, your watch ticking at a crawl. But from your own perspective, time would seem to flow normally, while the distant universe would appear to speed up around you. The strength of gravity depends on both mass and distance. Newton's law tells us that gravitational force increases with the mass of the objects involved and decreases with the square of the distance between them. This means that doubling the mass of an object doubles the gravitational force it exerts, while doubling the distance reduces the force to 1/4 of its original strength. This relationship has profound implications. The Sun, though vastly more massive than the Moon, exerts only about half the tidal force on Earth because it is so much farther away. The gravitational pull you feel from a mountain when standing at its base is incredibly weak, because, despite the mountain's enormous mass, most of that mass is distributed at various distances and directions from you, and the effects mostly cancel out. Every object with mass attracts every other object. This universal nature of gravity means that you exert a gravitational pull on every other person, every building, every planet, and every star in the universe. The book on your nightstand pulls slightly on the moon. The moon pulls slightly on the book. The force is unimaginably small for ordinary objects, far too weak to measure with everyday instruments, but it exists nonetheless. When you walk past another person, there is a minuscule gravitational attraction between you. If you could somehow eliminate all other forces, you would very, very slowly drift toward each other. Of course, in reality, the electromagnetic forces between molecules, air resistance, and countless other effects dwarf this tiny gravitational tug. But it's there, connecting you to everything in the cosmos through invisible threads of attraction. The gravitational constant G is a fundamental number in physics. This constant appears in Newton's law of gravitation and determines the strength of the gravitational force. Its value is approximately 6.67 times 10 to the minus 11th cubic meters per kilogram per second squared. This extraordinarily small number reflects just how weak gravity truly is. Measuring G accurately has proven remarkably difficult. Even today, it remains one of the least precisely known fundamental constants. The first successful measurement was made by Henry Cavendish in 1798, using a delicate torsion balance to measure the faint gravitational attraction between lead spheres. Modern experiments still use variations of this basic approach, attempting to measure the invisible pull between masses in the laboratory, while isolating the apparatus from every possible disturbance, from seismic vibrations to air currents, to the gravitational influence of nearby mountains. Gravity creates tides in Earth's oceans. The Moon's gravitational pull is stronger on the side of Earth facing it than on the opposite side. This difference in gravitational force stretches Earth slightly, creating bulges in the ocean on both the near and far sides. As Earth rotates beneath these bulges, most coastal areas experience 2 high tides and 2 low tides each day. The Sun also contributes to tides, though its effect is about half that of the Moon, despite being far more massive because it's so much farther away. When the Sun, Earth and Moon align during new and full moons, their gravitational pulls combine to create especially high spring tides. When they form a right angle during quarter moons, they partially cancel each other, producing gentler neap tides. The tides we observe are not just simple water bulges, but complex phenomena shaped by the depth and shape of ocean basins, the rotation of the Earth, and the friction between water and the seafloor. In some locations, like the Bay of Fundy in Canada, the tidal range can exceed 16 meters, while in other places it may be less than a meter. These variations arise from the way ocean water sloshes back and forth in basins of different shapes and sizes, creating resonances that amplify or diminish the basic tidal forces. Tidal forces can tear objects apart. As you approach a massive object like a black hole, the difference in gravitational pull between your head and feet becomes extreme. If you fell feet first toward a black hole, the gravity pulling on your feet would be vastly stronger than the gravity at your head. This differential force would stretch you vertically while simultaneously compressing you horizontally. Astrophysicists have given this gruesome process a whimsical name: spaghettification. You would be stretched into a long, thin strand before ultimately being torn apart. The same tidal forces work on a gentler scale throughout the universe. The Moon's tidal pull on Earth creates friction that gradually slows Earth's rotation, making our days slightly longer over millions of years. Meanwhile, this same interaction causes the Moon to slowly drift away from Earth at a rate of about 3.8 centimeters per year. Gravity is responsible for the formation of stars. In the early universe, clouds of hydrogen gas drifted through space. Gravity drew these atoms together, pulling denser regions into even tighter clumps. As these clouds collapsed under their own weight, the gas in their centers grew hotter and denser. When the temperature and pressure reached critical levels, nuclear fusion ignited and a star was born. This balance between gravity's inward pull and the outward pressure from fusion reactions is what keeps stars shining steadily for millions or billions of years. Gravity is the sculptor that transforms diffuse gas into blazing suns, the force that lights up the darkness of space. Every star you see in the night sky, every sun warming a distant world, every brilliant beacon across the cosmos exists because gravity gathered matter together and compressed it until it caught fire. Planets and moons form through gravitational collapse. Around young stars, disks of dust and gas swirl in orbit. Within these protoplanetary disks, tiny particles collide and stick together, forming larger and larger clumps. As these clumps grow, their gravity strengthens, allowing them to pull in more material. Over millions of years, this process builds planets, moons, and asteroids. The larger objects dominate their neighborhoods, sweeping up nearby debris or flinging it away. Earth, Mars, Jupiter, Saturn, all the worlds in our solar system coalesced from a spinning disk of material through this gradual gravitational accumulation. The same process is happening right now around young stars throughout the galaxy, building planetary systems in clouds of dust illuminated by newborn light. Gravity keeps planets in orbit around the sun. Without gravity, planets would fly off into interstellar space in straight lines, following Newton's first law of motion. But the sun's immense gravitational pull constantly bends their paths, curving their straight-line motion into elliptical orbits. The planets are perpetually falling toward the sun, but they're also moving sideways fast enough that they keep missing it, falling around it instead. This beautiful balance creates the stable orbits that have persisted for billions of years. Each planet's orbital speed is precisely tuned to its distance from the sun. Mercury, close to the sun's intense gravitational field, races around its orbit at 47 kilometers per second. Distant Neptune, where the sun's gravity is far weaker, crawls along at just 5.4 kilometers per second, taking 165 Earth years to complete a single orbit. Newton realized that this same principle applies to the Moon orbiting Earth and to any projectile launched from Earth's surface. If you could throw a ball fast enough horizontally, it would fall around Earth rather than into it, becoming an artificial satellite. This insight unified terrestrial and celestial mechanics, showing that the same laws govern both falling apples and orbiting moons. The orbital velocity needed to circle Earth at low altitude is about 8 kilometers per second. Below this speed, an object falls back to Earth. Above it, the object enters a stable orbit, endlessly falling around the planet. The Moon's gravity is about 1/6 as strong as Earth's. Because the Moon has much less mass than Earth, roughly 1/81st, an object on the lunar surface weighs only 1/6 of what it weighs on Earth. This is why Apollo astronauts could leap so high and bound across the lunar landscape in graceful, slow-motion arcs. A person who weighs 180 pounds on Earth would weigh only 30 pounds on the Moon, but their mass would remain the same. The confusion between weight and mass is common. Mass is the amount of matter in an object and never changes. Weight is the force that gravity exerts on that mass and varies depending on the strength of the gravitational field. An astronaut on the Moon has the same mass as on Earth, but weighs much less because the Moon's weaker gravity pulls on that mass with less force. Astronauts in orbit are not in zero gravity. This is one of the most persistent misconceptions about spaceflight. The International Space Station orbits about 400 kilometers above Earth's surface, where gravity is still about 90% as strong as at sea level. Astronauts float not because gravity has vanished, but because they are in continuous freefall. The space station and everything inside it are falling toward Earth, but moving forward so fast that they keep missing the planet, falling around it instead. This is what an orbit really is, falling around a body rather than into it. Because the astronauts and the station are falling together at the same rate, there is no force between them, creating the sensation of weightlessness. They experience microgravity, not zero gravity. In this state of endless falling, a dropped object doesn't fall to the floor, because everything is falling together through the same curved space-time. Free fall creates the feeling of weightlessness. When you stand on Earth's surface, you feel weight because the ground pushes up against your feet, opposing gravity's downward pull. Your body registers this compression as weight. In an elevator, if the cable broke and you began falling, both you and the elevator would accelerate downward at the same rate. There would be no floor pushing up on your feet, no compression, no sensation of weight. You would feel weightless, even though gravity is pulling on you exactly as before. This is the same experience astronauts have in orbit. They and their spacecraft are in free fall together, so they feel no floor, no support, no weight. The feeling of floating is really the feeling of falling endlessly around the world. This equivalence between free fall and weightlessness was central to Einstein's thinking. He realized that someone in a closed elevator could not tell whether they were floating in deep space, far from any gravitational sources, or falling freely in a gravitational field. Both situations would feel identical. This thought experiment led him to the equivalence principle, the insight that gravity and acceleration are fundamentally related, which became the foundation of general relativity. Astronauts aboard the International Space Station spend months experiencing this continuous freefall, which has various effects on the human body. Muscles atrophy without the need to support weight against gravity. Bones lose density because they're not bearing loads. Fluids redistribute differently throughout the body, causing faces to appear puffy. These changes demonstrate how deeply adapted we are to living in Earth's gravitational field. Gravity creates the force we call weight. Weight is simply the measure of how hard gravity pulls on your mass. On Earth, your weight is the product of your mass and Earth's gravitational acceleration, approximately 9.8 meters per second squared. If you traveled to a different planet, your mass stays the same, but your weight changes because the gravitational acceleration is different. On Jupiter, with its immense mass, you would weigh more than twice what you do on Earth. On Mars, with its smaller mass, you would weigh only about 1/3 of your Earth weight. This is why scales measure weight in pounds or newtons, units of force, while mass is measured in kilograms. When you step on a scale, you're measuring how hard Earth's gravity pulls you down against it. Black holes are regions where gravity becomes infinitely strong. When a massive star exhausts its nuclear fuel, it can collapse under its own gravity, compressing so much mass into such a small space that space-time curves beyond any limit. The result is a black hole, a region where gravity is so intense that nothing, not even light, can escape if it crosses a boundary called the event horizon. At the center lies a singularity, a point where our understanding of physics breaks down and the equations of general relativity predict infinite density. Black holes are not cosmic vacuum cleaners, indiscriminately sucking in everything around them. Their gravitational pull follows the same rules as any other mass. If the Sun suddenly became a black hole of the same mass, Earth would continue orbiting exactly as before. The difference is what happens close to them, within a few times their radius, where gravity becomes overwhelmingly powerful. Astronomers detect black holes indirectly through their effects on nearby matter. Gas falling toward a black hole heats up and emits intense radiation before crossing the event horizon. Binary systems where a normal star orbits an invisible massive companion can reveal stellar mass black holes. The orbital motions of stars near galactic centers betray the presence of supermassive black holes millions or billions of times the mass of the Sun. The event horizon is the point of no return around a black hole. This spherical boundary marks the distance from a black hole where the escape velocity equals the speed of light. Outside the event horizon, though gravity is strong, escape is still theoretically possible. Inside, even light cannot climb back out against the pull of gravity. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of the Sun, the event horizon would have a radius of about 3 kilometers. For the supermassive black hole at the center of our galaxy, which contains the mass of 4 million suns, the event horizon stretches across a diameter of about 24 million kilometers. Interestingly, for supermassive black holes, the gravitational force at the event horizon can actually be relatively weak, allowing objects to cross without being torn apart, though they can never return. Gravitational waves are ripples in space-time. When massive objects accelerate, particularly when they orbit or collide with each other, they create disturbances in the fabric of space-time that propagate outward at the speed of light. These gravitational waves are like ripples spreading across a pond, except they're ripples in the very geometry of space and time. As a gravitational wave passes through a region, it alternately stretches and compresses space in perpendicular directions, causing the distance between objects to oscillate by incredibly tiny amounts. Albert Einstein predicted their existence in 1916, but thought they would be far too weak to ever detect. For a century, they remained a theoretical curiosity, an untested prediction of general relativity, until technology finally advanced enough to prove Einstein right. Unlike electromagnetic waves, which are oscillations of electric and magnetic fields, gravitational waves are oscillations in space-time itself. They pass through matter almost completely unimpeded, carrying information about cosmic events from across the universe without being absorbed or scattered along the way. This makes them a unique messenger, allowing us to observe phenomena that produce little or no light. LIGO detected gravitational waves for the first time in 2015. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory recorded a signal that had traveled more than 1 billion light-years across the universe. Two black holes, one 29 times the mass of the Sun and the other 36 times solar mass, had spiraled into each other and merged, releasing energy equivalent to 3 solar masses in a fraction of a second. The power output of this collision briefly exceeded that of all the stars in the visible universe combined. Yet, by the time the gravitational waves reached Earth, they were so weak that they changed the 4-kilometer length of LIGO's detector arms by less than 1/10,000th the width of a proton. This detection opened an entirely new way of observing the universe, allowing us to witness events that produce no light, no electromagnetic radiation, only the silent ringing of space-time itself. The observation was made at 2 separate facilities, one in Louisiana and one in Washington State, separated by about 3,000 kilometers. The signal arrived at the 2 detectors 7 milliseconds apart, allowing scientists to determine roughly where in the sky the event occurred. Since that first detection, LIGO and its European counterpart, Virgo, have observed dozens of similar events, revealing a universe rich with colliding black holes and neutron stars. Gravitational waves travel at the speed of light. This was confirmed by LIGO's observations and provides powerful evidence for Einstein's theory. When 2 neutron stars collided in 2017, producing both gravitational waves and a burst of light, both signals arrived at Earth almost simultaneously after traveling 130 million light-years. The tiny time difference between their arrivals was consistent with the waves and light, taking slightly different paths through space and arriving from different locations in the merged system. This observation proved that gravitational waves propagate at the speed of light to within 1 part in 10 to the 15th power, an extraordinarily precise confirmation. It also demonstrated that gravity and light share the same cosmic speed limit, the maximum speed at which information can travel through the universe. Every mass creates a gravitational field around it. This field permeates the space surrounding the mass, growing weaker with distance but extending infinitely in all directions. The gravitational field is a way of describing how the presence of mass warps space-time, creating a landscape of curves and slopes that other masses respond to. You can visualize it as a 3-dimensional map of how strongly gravity pulls at different locations around an object. Near Earth's surface, the gravitational field points downward toward the planet's center and has a strength of about 9.8 newtons per kilogram. As you climb higher, the field weakens gradually. On top of Mount Everest, it's about 9.77 newtons per kilogram. Aboard the International Space Station, it's still about 8.7 newtons per kilogram. Even far out in space, Earth's gravitational field never quite disappears, though it becomes vanishingly weak. Gravitational potential energy increases with height. When you lift an object against gravity's pull, you do work on it, storing energy in the object's position. This stored energy is called gravitational potential energy. The higher you lift it, the more energy you store. If you drop the object, this potential energy converts into kinetic energy as it falls, speeding up until it hits the ground. This transformation between potential and kinetic energy explains everything from flowing rivers to falling rain to the operation of grandfather clocks. Water stored behind a dam possesses enormous gravitational potential energy by virtue of its height. When released, this energy can turn turbines and generate electricity. The same principle explains why a roller coaster climbs to a great height at the start of the ride, storing potential energy that will later transform into the thrilling kinetic energy of the descent. Escape velocity is the speed needed to break free from gravity. For Earth, this speed is about 11.2 kilometers per second, or roughly 40,000 kilometers per hour. Launch a projectile upward at this speed, and it will have enough kinetic energy to completely escape Earth's gravitational pull, continuing outward into space forever. Launch it slower, and it will eventually fall back. Escape velocity decreases as you get farther from Earth because gravity weakens with distance. This is why rockets don't need to achieve escape velocity at ground level. They can climb gradually, expending fuel to fight gravity a little at a time. The Moon's escape velocity is only 2.4 kilometers per second, which is why Apollo astronauts could leave the lunar surface with a relatively small rocket engine. Escape velocity also explains why massive planets retain thick atmospheres while smaller worlds lose theirs. Molecules in a hot atmosphere move randomly at various speeds. If some exceed the escape velocity, they fly off into space, never to return. This is why Mars, with its lower escape velocity and weaker gravity, has lost most of its original atmosphere over billions of years, while Earth has retained its protective blanket of air. The concept applies to all gravitational systems, from asteroids to stars to entire galaxies, each with its own escape velocity determined by its mass and size. Neutron stars have extreme gravitational fields. When a massive star explodes as a supernova, it can leave behind a core so dense that protons and electrons merge into neutrons. The result is a neutron star, typically just 20 to 25 kilometers across, but containing more mass than the Sun. The gravity at a neutron star's surface is about 200 billion times stronger than Earth's. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. If you could somehow stand on a neutron star, you would be instantly flattened into a layer a few atoms thick by the immense gravity. Mountains on neutron stars are believed to be only millimeters high, because gravity is too strong to support any larger irregularities. The intense gravitational field bends light dramatically, allowing you to see part of the star's far side by looking over the edge as light curves around from behind. If the neutron star is spinning rapidly, its gravity drags space-time around with it in a phenomenon called frame dragging. Some neutron stars rotate hundreds of times per second, their surfaces moving at a significant fraction of the speed of light. These rapidly spinning neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse, and if Earth happens to lie in the path, we detect regular pulses of radio waves or other radiation. The precise timing of these pulses makes pulsars among the most accurate clocks in the universe. Frame dragging is the twisting of space-time by rotating objects. According to general relativity, a spinning mass not only curves space-time but also drags it along in the direction of rotation, like a marble spinning in honey. The Gravity Probe. B satellite, launched in 2004, was designed to detect this twisting of space around our planet by observing the precession of ultra-precise gyroscopes. The mission successfully measured this effect, confirming Einstein's prediction. Near a rapidly rotating black hole or neutron star, frame dragging becomes far more dramatic. Close to such an object, you would find it impossible to remain stationary. Space itself is being dragged in circles, and you would be carried along with it, forced to orbit whether you wanted to or not. This region where rotation becomes mandatory is called the ergosphere, and it exists outside the event horizon of a rotating black hole. Gravity affects time differently at different heights. A clock on Earth's surface runs slower than an identical clock at high altitude because it sits in a stronger gravitational field. This effect is small but real and measurable. If you lived on the ground floor of a tall building while your twin lived on the top floor, you would age very slightly slower than your twin. The difference would be impossibly small, perhaps microseconds over a lifetime, but it exists. This gravitational time dilation has been precisely measured using atomic clocks. In one experiment, physicists placed identical atomic clocks at different heights and confirmed that the higher clock indeed ran faster. The effect increases dramatically near massive objects. Near the event horizon of a black hole, time slows so much that to an outside observer, an object falling in would appear to freeze at the horizon, gradually fading from view as its light becomes increasingly redshifted. Gravitational redshift is the stretching of light by gravity. As light climbs out of a gravitational field, it loses energy, which manifests as a shift toward longer, redder wavelengths. This gravitational redshift was one of the early tests of general relativity. In the 1960s, physicists Robert Pound and Glenn Rebka measured the tiny redshift of gamma rays traveling up just 22.5 meters in a tower at Harvard University, confirming Einstein's prediction. The same effect explains why light from the surface of white dwarfs and neutron stars appears significantly redshifted. From inside the gravitational well of a massive object, time runs slower, so light appears to be emitted at a lower frequency when observed from far away, where time runs faster. This interplay between gravity, time, and light reveals the deep connection between these fundamental aspects of reality that Einstein's theory so elegantly describes. The center of gravity is the average position of an object's mass. For a uniform sphere, it's the geometric center. For an irregularly shaped object, it might be located outside the object itself. The center of gravity is the point around which an object's mass is evenly distributed, the point where you could balance it on a fingertip. When an object rotates or tumbles through space, it spins around its center of gravity. When you calculate the gravitational interaction between two objects, you can often simplify the problem by treating each object as if all its mass were concentrated at its center of gravity. This is why we can model Earth and the Moon as point masses when calculating their orbital mechanics, even though they're extended bodies with complex internal structures. Gravitational lensing can magnify distant galaxies. When light from a very distant galaxy passes through the gravitational field of a massive foreground object, such as a galaxy cluster, the light's path curves around the cluster. This bending can focus the light, acting like a cosmic magnifying glass. Sometimes the background galaxy appears magnified and brightened, allowing astronomers to study objects that would otherwise be too faint to observe. Other times, the lensing creates multiple images of the same distant galaxy, or stretches it into arcs and rings. The Hubble Space Telescope has captured spectacular images of these gravitational lenses, showing distant galaxies warped into graceful curves around foreground clusters. This natural telescope allows us to peer deeper into space and further back in time than would otherwise be possible, studying galaxies as they appeared when the universe was young. Strong gravitational lensing can create Einstein rings. When a background source, a massive lens, and the observer are perfectly aligned, the light from the source is bent around the lens in all directions equally, creating a complete ring of light around the lensing object. These Einstein rings, named in honor of the physicist who predicted them, are relatively rare because the alignment must be precise. But when they occur, they create some of the most beautiful and surreal images in astronomy. The ring is not a physical structure, but a mirage, an image of a single distant galaxy wrapped around an intervening mass. By studying the shape and brightness of these rings, astronomers can map the distribution of matter in the lensing galaxy, including dark matter that cannot be seen directly. Weak gravitational lensing reveals dark matter. Even when lensing isn't strong enough to create obvious distortions, it subtly stretches the shapes of distant galaxies in statistically measurable ways. By analyzing the shapes of thousands of background galaxies, astronomers can map the distribution of mass in foreground structures, even when most of that mass is invisible dark matter. This technique has revealed vast cosmic webs of dark matter connecting galaxy clusters, and confirmed that most of the matter in the universe doesn't emit or absorb light. The subtle distortions tell us where mass exists, even when we cannot see it, like inferring the shape of an invisible sculpture by observing how it bends the light passing around it. Microlensing can detect planets around other stars. If a star passes in front of a more distant star from our perspective, the foreground star's gravity can act as a lens, briefly brightening the background star if the foreground star has a planet orbiting it. The planet's gravity can create a small additional brightening blip in the light curve. This technique, called gravitational microlensing, has discovered dozens of exoplanets that would be impossible to detect by other methods. It's particularly sensitive to planets far from their host stars, complementing other detection techniques. The lensing events are unpredictable and brief, typically lasting weeks or months, so astronomers must monitor millions of stars continuously, waiting for the rare alignment that reveals a planet's presence. Gravity is the same for all objects regardless of their composition. This is the equivalence principle, one of the deepest insights about gravity. A feather and a hammer released simultaneously in a vacuum fall at exactly the same rate, regardless of their different masses and materials. This was famously demonstrated by Apollo 15 astronaut David Scott on the Moon in 1971. In the airless lunar environment, the feather and hammer hit the ground simultaneously, just as Galileo had predicted 4 centuries earlier. This universal response to gravity is fundamentally different from any other force. It's a unique property that hinted to Einstein that gravity might not be a force at all, but a feature of space-time geometry. All objects follow the same curved paths through space-time, regardless of what they're made of or how massive they are. The gravitational pull of the Earth is not perfectly uniform. Earth is not a perfect sphere. It bulges at the equator due to its rotation, and its mass is distributed unevenly, with denser material in some regions than others. Mountains add extra mass locally, while ocean trenches represent regions of less mass. These variations create slight differences in the strength of gravity across Earth's surface. Satellites mapping Earth's gravity field have revealed a complex pattern of hills and valleys in the gravitational landscape. These variations are tiny, typically less than 1% of the overall field strength, but they affect the orbits of satellites and can be used to study Earth's interior structure and the flow of material in the mantle. The Moon is slowly moving away from Earth. Tidal interactions between Earth and the Moon transfer angular momentum from Earth's rotation to the Moon's orbit. This causes Earth to rotate more slowly, lengthening our day by about 2 milliseconds per century, while the Moon drifts farther away at about 3.8 centimeters per year. Billions of years ago, the Moon was much closer, and the day was much shorter. Coral fossils preserve daily and yearly growth rings that allow scientists to count the number of days in a year in the distant past, confirming that Earth rotated faster. In the far future, this process will continue until Earth's rotation becomes tidally locked to the Moon's orbit, with each rotation of Earth taking as long as one lunar orbit. At that point, the same side of Earth would always face the Moon, and the Moon would hang motionless in the sky as seen from that hemisphere. Tidal locking causes one side of the Moon to always face Earth. The same process that is slowly locking Earth's rotation to the Moon has already locked the Moon's rotation to Earth. Early in the Moon's history, Earth's gravity created tidal bulges in the Moon's rocky body. As the Moon rotated, these bulges moved around the Moon, but the friction from this movement gradually slowed the Moon's rotation. Eventually, the Moon's rotation period became equal to its orbital period around Earth, about 27.3 days. Now the same hemisphere always faces Earth, while the far side remains forever hidden from our direct view. This synchronous rotation is common for moons throughout the solar system and for planets orbiting close to their stars. It's a natural outcome of the tidal forces that occur when one gravitational body influences another over long periods. Lagrange points are locations where gravitational forces balance. In a system with two massive bodies, such as Earth and the Sun, there are 5 special points where a smaller object can orbit in a stable or semi-stable configuration, maintaining a fixed position relative to the two larger bodies. These are called Lagrange points. The L1 point lies between the two masses, where their gravitational pulls balance. Several spacecraft have been stationed at the Earth-Sun L1 point to observe the Sun without Earth blocking the view. The L2 point lies beyond the smaller mass, away from the larger one. The James Webb Space Telescope orbits the Earth-Sun L2 point, keeping its instruments cold in the permanent shadow of its sunshield. The L4 and L5 points form equilateral triangles with the two masses and can collect dust and asteroids over time. Jupiter has thousands of Trojan asteroids orbiting at its L4 and L5 points. The Sun's gravity holds the entire solar system together. Our star contains 99.86% of the solar system's total mass, and its gravitational dominance extends far beyond the planets. The most distant known objects in the solar system, some orbiting 10,000 times farther from the Sun than Earth, still feel the Sun's gravitational pull and follow elliptical paths around it. The Sun's gravitational influence defines a sphere called the Hill sphere, within which objects are primarily influenced by the Sun, rather than the gravity of other stars. Beyond this region, interstellar gravity becomes more important. The boundary lies perhaps 1 or 2 light years from the Sun, roughly halfway to the nearest stars. Everything within this vast sphere of influence is part of our solar system, bound to the Sun by invisible threads of gravity that will hold them for billions of years. Supermassive black holes lurk at the centers of most galaxies. Our Milky Way galaxy harbors a black hole with the mass of 4 million suns at its center, about 26,000 light-years from Earth. Other galaxies contain even more massive central black holes, some weighing billions of solar masses. These cosmic monsters grow by consuming gas, stars, and other black holes over billions of years. When material falls towards such a black hole, it forms a swirling accretion disk that heats to millions of degrees, emitting enormous amounts of radiation. The most luminous objects in the universe, quasars, are powered by supermassive black holes in the centers of young galaxies, accreting materials so rapidly that they outshine all the stars in their host galaxy combined. Despite their immense mass, these black holes occupy a relatively small volume. The event horizon of even a billion solar mass black hole would fit comfortably within our solar system. Gravity creates the large-scale structure of the universe. In the early universe, tiny variations in the density of matter, perhaps 1 part in 100,000, seeded the growth of structure. Regions that were slightly denser had slightly stronger gravity, which pulled in more matter, making them denser still. Over billions of years, this gravitational instability amplified the initial fluctuations, transforming nearly uniform gas into an intricate cosmic web of galaxies, clusters, and vast filaments separated by enormous voids. The pattern we observe today in the distribution of galaxies across the universe is a direct result of gravity, acting on primordial density variations. Computer simulations that include only gravity and the known properties of matter and dark energy can reproduce the observed large-scale structure with remarkable accuracy, confirming our understanding of how cosmic structure forms. Dark matter is detected only through its gravitational effects. Observations of galaxies and galaxy clusters reveal that the visible matter, the stars and gas that emit or absorb light, accounts for only a small fraction of the total mass. The rotation curves of spiral galaxies show stars orbiting far faster than they should, if only visible matter were present. In the 1970s, astronomer Vera Rubin measured the speeds of stars at various distances from galactic centers and found that they maintained roughly constant velocities even far from the visible disk, rather than slowing down as expected. Galaxy clusters contain too little visible matter to hold themselves together gravitationally. The galaxies within clusters move so fast that the clusters should fly apart, unless there's far more mass present than we can see. The gravitational lensing around clusters is far stronger than the visible mass could produce, bending light from background galaxies more than the observed stars and gas could account for. All these observations point to the existence of dark matter, a form of matter that doesn't interact with light but does exert and respond to gravity. Dark matter appears to outweigh visible matter by about 5 to 1, making up roughly 85% of all matter in the universe. Its nature remains one of the greatest mysteries in physics. Despite decades of searching, no one has directly detected a dark matter particle, though experiments deep underground and in space continue the hunt. Leading candidates include weakly interacting massive particles, or WIMPs, and axions. But the true identity of dark matter remains unknown. Dark energy is accelerating the expansion of the universe. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe is not slowing down due to gravity, as many expected, but speeding up. This discovery implies the existence of dark energy, a mysterious form of energy that permeates all of space and exerts a kind of negative pressure, pushing the universe to expand faster and faster. Dark energy appears to make up about 68% of the total energy content of the universe, dominating over both dark and visible matter. Its nature is completely unknown. It might be the energy of empty space itself, a quantum field permeating the vacuum, or something even stranger. Understanding dark energy is one of the biggest challenges in modern cosmology and may require new physics beyond our current theories of gravity and quantum mechanics. Gravitational potential creates gravitational wells. You can visualize the gravitational field around a massive object as a well, a depression in the fabric of space-time. The deeper the well, the stronger the gravitational pull. Earth sits in the Sun's gravitational well, The moon sits in Earth's well within the sun's larger well, and so on in nested structures. To escape from a gravitational well requires energy. Spacecraft leaving Earth must climb out of our planet's well, expending fuel to gain the altitude and velocity needed to break free. Gravity assists, where a spacecraft swings around a planet to gain speed, can be understood as the spacecraft falling into the planet's gravitational well and then being flung back out, carrying extra momentum borrowed from the planet's orbital motion. These slingshot maneuvers have enabled missions to the outer solar system and beyond. Artificial gravity can be created by rotation. While we cannot turn gravity on and off or generate it artificially, we can create a force that feels like gravity through rotation. If a spacecraft or space station rotates, the centrifugal force pushing outward against the rotating structure mimics gravity's inward pull. Walk on the inner surface of a rotating cylinder and you'll feel pressed down against it as if by gravity. The faster the rotation, the stronger the simulated gravity. However, if the rotating structure is small, there can be significant differences in the force felt by your head versus your feet. And turning your head can create disorienting Coriolis effects. Science fiction often depicts large rotating space stations that could provide comfortable artificial gravity for their inhabitants, though no such structures have yet been built. It remains a promising approach for long-duration space missions and potential space settlements. Gravitational time dilation affects GPS satellites. The satellites orbiting Earth experience weaker gravity than clocks on the ground, causing their onboard atomic clocks to run faster by about 45 microseconds per day due to gravitational time dilation. However, they're also moving at about 14,000 kilometers per hour relative to observers on the ground. And according to special relativity, this motion causes their clocks to run slower by about 7 microseconds per day. The combined effect is that GPS satellite clocks run about 38 microseconds per day, faster than Earth-based clocks. This may sound insignificant, but light and radio signals travel about 30 centimeters in a nanosecond. Without correcting for relativistic effects, GPS positions would drift by about 11 kilometers per day, rendering the system useless for navigation. The system compensates by adjusting the frequency of the satellite clocks before launch. The clocks are set to tick at a slightly slower rate on the ground, so that when they reach orbit and experience the combined relativistic effects, they tick at the same rate as clocks on the ground. This daily application of both general and special relativity in a technology millions of people use demonstrates that these effects, while small, are real and measurable. GPS is often cited as one of the most practical demonstrations that Einstein's theories of relativity are not just abstract physics, but describe the actual behavior of clocks and time in our universe. Gravity powers quasars, the most luminous objects in the universe. When matter falls into a supermassive black hole, it releases gravitational potential energy, heating the infalling gas to millions of degrees and causing it to radiate intensely. This process is incredibly efficient, converting up to 40% of the infalling mass into energy. far more efficient than nuclear fusion, which converts less than 1%. A supermassive black hole consuming the equivalent of 10 solar masses per year can shine with the power of 100 trillion suns, brighter than an entire galaxy. These objects, called quasars or active galactic nuclei, were common in the early universe when galaxies were still forming and merging, providing abundant fuel for their central black holes. Today, they're rare, though most galaxies may have gone through a quasar phase in their youth. Gravitational collapse can create a supernova. When a massive star exhausts its nuclear fuel, the core that had been supported by fusion reactions suddenly collapses under its own gravity. The collapse happens in less than a second, compressing a core the size of Earth to a neutron star just 20 kilometers across. The infalling material rebounds off this incredibly dense core, generating a shock wave that blows the rest of the star apart in a supernova explosion. For a few weeks, the exploding star can shine as brightly as an entire galaxy. These explosions seed the cosmos with heavy elements forged in the star's core and in the explosion itself, scattering iron, gold, uranium, and every element heavier than hydrogen and helium into space, where they can eventually incorporate into new stars and planets. Everything on Earth heavier than helium was created in such stellar furnaces and dispersed by gravity's final crushing embrace. The equivalence principle states that gravity and acceleration are indistinguishable. Einstein's insight was that a person in a closed elevator being accelerated upward would feel exactly the same force as someone standing in a gravitational field. There's no experiment you could perform inside the elevator to tell the difference. This equivalence between gravitational and inertial mass, between the mass that responds to gravity and the mass that resists acceleration, is not obvious. There's no reason they should be the same quantity, and yet experiments show they are identical to at least 1 part in 10 trillion. This deep connection between gravity and acceleration led Einstein to his geometric interpretation of gravity. If you cannot distinguish between acceleration and gravity, perhaps gravity is a form of acceleration, an acceleration through curved space-time. Gravitational potential energy is converted to kinetic energy in falling objects. When you release a ball from your hand, gravity accelerates it downward, converting the potential energy of its elevated position into the kinetic energy of motion. As it falls, it moves faster and faster, accumulating kinetic energy. When it hits the ground, this kinetic energy is converted into sound, heat, and the deformation of both the ball and the ground. The total energy is conserved throughout the process, transforming from one form to another but never disappearing. This principle explains phenomena from the flow of rivers to the impact of meteorites. Water at the top of a waterfall has high potential energy. As it cascades down, that energy transforms into kinetic energy and then into the mist and sound of the waterfall. A meteorite entering Earth's atmosphere has both kinetic energy from its motion and gravitational potential energy from its height. And this enormous energy is converted into heat and light as it plunges through the air. Every planet's gravity is different. Mars, with about 11% of Earth's mass, has a surface gravity of about 3.7 meters per second squared, roughly 38% of Earth's. On Mars, you could jump nearly 3 times as high as on Earth. Jupiter, with 318 times Earth's mass, but also much larger radius, has a surface gravity of about 25 meters per second squared, 2.5 times Earth's. On Jupiter's cloud tops, you would weigh more than twice your Earth weight, making every movement exhausting. Venus and Earth have similar sizes and masses, so their surface gravities are nearly identical. The diversity of gravitational environments in our solar system provides natural laboratories for understanding how gravity affects everything, from the retention of atmospheres to the shapes of planetary bodies to the potential for human exploration and settlement. Tidal heating can melt moons from the inside. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of active volcanoes on its surface, despite being smaller and colder than Earth. The heat driving this activity comes from tidal flexing. As Io orbits Jupiter in an elliptical path, the giant planet's gravity squeezes and stretches the moon, alternately compressing and relaxing its interior. This constant kneading generates enormous amounts of friction and heat, keeping Io's interior molten. Saturn's moon Enceladus experiences similar tidal heating, though less extreme, which melts ice beneath its surface and powers geysers of water vapor that spray hundreds of kilometers into space. This tidal heating can create habitable environments inside moons that are far from the sun's warmth, expanding the possibilities for life in our solar system and beyond. Gravity determines the maximum height of mountains. On Earth, mountains can only grow so tall before their own weight causes the rock beneath them to flow like a very viscous fluid, a process called isostasy. The maximum sustainable height depends on the strength of the rock and the surface gravity. On a world with stronger gravity, mountains would be shorter because the weight pressing down on their base would be greater. On a world with weaker gravity, mountains could be much taller. Mars, with its lower surface gravity, hosts Olympus Mons, the largest volcano in the solar system, rising 21 kilometers above its base. This mountain, nearly 2.5 times the height of Mount Everest, could not exist on Earth. Its enormous mass would cause it to sink into the Martian crust if Earth's stronger gravity applied. Gravitational assists have enabled missions to the outer solar system. When a spacecraft passes close to a planet, it can gain or lose orbital energy through a gravitational slingshot maneuver. As the spacecraft approaches the planet, it falls into the planet's gravitational well, gaining speed. If the trajectory is carefully planned, the spacecraft can be flung out in a different direction, carrying away momentum borrowed from the planet's orbital motion around the Sun. The planet slows down infinitesimally in its orbit, while the spacecraft gains a significant boost. The Voyager spacecraft used gravitational assists from Jupiter and Saturn to reach Neptune and explore the outer solar system. The Cassini mission to Saturn performed flybys of Venus, Earth, and Jupiter to gain the velocity needed to reach the ringed planet. These maneuvers are essential for deep space exploration because they allow spacecraft to reach destinations that would otherwise require impossibly large amounts of fuel. Orbital resonances create stable patterns in planetary systems. When the orbital periods of two bodies are related by a simple fraction, such as 1 to 2 or 2 to 3, they're in orbital resonance. Each time the bodies return to the same relative configuration, they exert gravitational pulls that reinforce rather than cancel over time. Sometimes these resonances destabilize orbits, clearing gaps. The gaps in Saturn's rings are often caused by resonances with Saturn's moons, where particles in those orbits are gradually perturbed into different paths. Other times, resonances stabilize orbits. Neptune's moon Triton and Pluto are in a 3 to 2 resonance, meaning Neptune orbits the Sun 3 times for every 2 of Pluto's orbits. And they never collide, even though their paths cross. The moons of Jupiter, Au, Europa, and Ganymede are locked in a complex resonance where their orbital periods are in a 4 to 2 to 1 ratio. These patterns create a gravitational dance that has persisted for billions of years. Gravitational binding energy holds celestial objects together. The energy required to completely disassemble an object into widely separated pieces is called its gravitational binding energy. For Earth, this amounts to about 2 times 10 to the 32nd joules, equivalent to about 1 week of the Sun's total energy output. For the Sun itself, the binding energy is vastly larger, about 4 times 10 to the 48th joules. This is the energy that must be released when a star forms from a diffuse cloud of gas, and it's the energy that would need to be supplied to tear a star apart. Gravitational binding energy explains why massive stars are so hot. As they form, enormous amounts of energy are released by gravitational collapse, heating the stellar core until fusion can begin. It also explains why supernovae are so powerful. The gravitational binding energy of a neutron star is so great that about 10% of the original star's mass is converted to energy in the collapse, powering the spectacular explosion. Micro black holes could theoretically exist. While stellar mass black holes form from collapsing stars and supermassive black holes reside in galactic centers, some theoretical models suggest that tiny black holes, perhaps no larger than subatomic particles, might have formed in the extreme conditions of the early universe. Stephen Hawking showed that such tiny black holes would emit thermal radiation due to quantum effects near their event horizons, a phenomenon called Hawking radiation. The smaller the black hole, the hotter it would be and the faster it would evaporate. A black hole with the mass of a mountain would be about the size of an atom and would evaporate in a fraction of a second in a burst of radiation. Based on these theoretical predictions, primordial black holes that formed in the early universe might still exist if they were massive enough to survive until today. Some scientists have explored whether dark matter could consist partly of such objects, though observations so far have not confirmed this possibility, leaving it as one intriguing idea among many competing theories. Hawking radiation suggests black holes could eventually evaporate. According to quantum mechanics, empty space isn't truly empty but filled with virtual particle pairs that constantly pop into and out of existence. Stephen Hawking theorized that near a black hole's event horizon, one particle of a pair might fall in while the other escapes. To an outside observer, it would appear that the black hole emitted a particle. This theoretical process, called Hawking radiation, implies that black holes would very slowly lose mass over time. If this theory is correct, a solar mass black hole would take about 10 to the 67 years to evaporate completely, far longer than the current age of the universe. The smaller the black hole, the faster it would evaporate, possibly ending in an explosive flash as the last bit of mass converts to energy. While Hawking radiation has not yet been observed directly, this theoretical framework links gravity, quantum mechanics, and thermodynamics in deep and profound ways that continue to guide research in theoretical physics. Space-time itself can have different geometries. In the absence of matter and energy, space-time is flat, following the rules of Euclidean geometry. Parallel lines never meet. The angles of a triangle sum to 180 degrees, and the circumference of a circle is exactly pi times its diameter. But the presence of mass and energy curves space-time, changing its geometry. Near a massive object, space becomes positively curved, like the surface of a sphere. On a sphere, parallel lines do meet. Triangle angles sum to more than 180 degrees, and circles have circumferences less than pi times their diameter. In regions of negative curvature, which don't occur in ordinary space-time but appear in some theoretical models, the opposite holds. Understanding the geometry of space-time is essential for understanding gravity, because gravity is the curvature, not a force propagating through space, but a feature of the very shape of space and time themselves. The geodesic is the straightest possible path through curved space-time. In flat space, a geodesic is simply a straight line. But in curved space-time, a geodesic curves, following the contours of the geometry. Objects not subject to any force follow geodesics through space-time. When you're in orbit, you're following a geodesic, a straight path through the curved geometry around Earth. You don't feel any force because you're moving naturally along the curve of space. When you stand on Earth's surface, the ground prevents you from following a geodesic, pushing you up and away from the natural path you would take if you were in freefall. This is why you feel weight. Your body wants to follow a geodesic straight down into Earth, but the electromagnetic forces in the ground's atoms push back, and you experience that resistance as weight. In the framework of general relativity, gravity doesn't pull you down. The ground pushes you up away from the geodesic path. General relativity predicts that energy also gravitates. In Newton's theory, only mass creates gravity. But Einstein showed that energy and mass are equivalent through the famous equation E equals mc squared. Since energy and mass are interchangeable, energy must also curve space-time and create gravitational effects. This means that light, which has energy but no rest mass, must both respond to gravity and create its own tiny gravitational field. The pressure inside the sun which represents energy, contributes to the Sun's total gravitational field. Even the gravitational field itself carries energy, and therefore curves space-time, leading to the complex nonlinear equations of general relativity. This prediction has been tested and confirmed in numerous ways, from the precise orbit of Mercury to the behavior of binary pulsars. Systems where two neutron stars orbit each other at speeds comparable to the speed of light, and where the energies involved are immense. Some theories propose modifications to gravity. While general relativity has passed every experimental test, it remains incomplete. It cannot be reconciled with quantum mechanics, and it requires dark matter and dark energy to explain observations. This has led some physicists to propose modified theories of gravity that might explain these phenomena without invoking new forms of matter or energy. Modified Newtonian dynamics, or MOND, suggests that gravity behaves differently at extremely low accelerations than Newton's law predicts. Other theories, like 4FR gravity or scalar tensor theories, modify Einstein's equations in various ways. None of these alternatives have gained widespread acceptance, because general relativity continues to match observations extremely well, and the modified theories often have their own problems. But the search for a better theory of gravity continues, driven by the hope of understanding dark matter and dark energy and unifying gravity with quantum mechanics. Quantum gravity is the attempt to unite general relativity and quantum mechanics. General relativity describes gravity beautifully on large scales, but treats space-time as smooth and continuous. Quantum mechanics describes the other forces at microscopic scales, but assumes space-time is a fixed, flat background. At the Planck scale, about 10 to the minus 35 meters, and 10 to the minus 43 seconds, both quantum effects and gravitational effects would become important, and our current theories break down. A complete theory of quantum gravity would describe how space-time itself behaves quantum mechanically. Different research programs explore various possibilities. Perhaps space and time are not continuous, but made of discrete units, or perhaps they emerge from more fundamental structures. String theory, loop quantum gravity, and other approaches attempt to build such a theory, but none have yet made testable predictions that distinguish them from general relativity in accessible regimes. If successful, quantum gravity might reveal the ultimate nature of black hole singularities, explain what happened at the Big Bang, and potentially unify all the forces of nature in a single mathematical framework. The gravitational constant might not be constant. Some theoretical frameworks suggest that fundamental constants of nature, including the gravitational constant g, might change very slowly over cosmic time. If this were true, and if g were larger in the early universe and has been decreasing, it could affect our understanding of cosmic evolution and the development of structure. Astronomers have searched for potential variations in g by studying ancient light from distant quasars and the orbital motions of planets and moons over decades. So far, observations have found no convincing evidence for variation. Current measurements constrain any change in g to less than 1 part in 1 trillion per year, suggesting it remains stable. The possibility of varying constants remains an area of theoretical research, because some approaches attempting to unify gravity with the other forces allow for such evolution, though observations continue to support constancy. Gravitons are the hypothetical particles that would carry the gravitational force. In quantum field theory, forces are mediated by particles. Electromagnetism is carried by photons, the weak force by W and Z bosons, the strong force by gluons. If gravity can be described quantum mechanically in a way similar to these other forces, it would also be carried by particles called gravitons. These would presumably be massless particles traveling at the speed of light, just like photons. But gravitons have never been detected and would likely be extraordinarily difficult to observe with any conceivable technology because the gravitational force is so weak. A single graviton would interact so feebly with matter that it would pass through detectors without leaving any trace. Whether gravitons truly exist depends on whether quantum mechanics applies to gravity in this particular way. The search for a consistent quantum theory of gravity is partly an attempt to understand whether gravitons exist, and if so, how they might give rise to the smooth, continuous curvature of space-time that we observe. Gravity shapes the evolution of stars. The life story of every star is a battle between gravity trying to compress it and internal pressure trying to expand it. When a star forms, gravity pulls gas together until the core becomes hot and dense enough for fusion to begin. The energy from fusion creates pressure that balances gravity, and the star settles into a stable state where it shines steadily for millions or billions of years. Eventually, the fuel runs out. For low-mass stars like the Sun, gravity gently compresses the core into a white dwarf, while the outer layers drift away. For massive stars, gravity wins more dramatically, crushing the core into a neutron star or black hole and triggering a supernova explosion. Gravity determines the star's ultimate fate based on its mass, scripting a cosmic drama that plays out over eons. The gravitational constant is one of the least precisely measured fundamental constants. While some constants, like the speed of light and Planck's constant, are known to 10 or more significant figures, the gravitational constant g is only known to about 5 significant figures. The difficulty lies in gravity's weakness. Measuring the attraction between laboratory-scale masses requires extraordinarily sensitive instruments isolated from every possible disturbance. The challenge is similar to measuring the faint attraction between 2 grains of sand from a distance of several kilometers, while accounting for the gravitational pull of every mountain, building, car, and person in the surrounding region. Different experiments measuring g have sometimes given results that don't quite agree within their stated uncertainties, suggesting there may be systematic errors we don't yet understand. Improving the precision of g is an ongoing effort in experimental physics. Gravity is essential to the existence of planets, stars, and galaxies. Without gravity, the universe would be a uniform, expanding cloud of gas, growing ever more diffuse as time passed. matter would never clump together to form any structures. There would be no stars to forge heavy elements, no planets to provide surfaces where chemistry could develop complexity, no galaxies to organize the cosmos into islands of light. Gravity is the cosmic architect, the force that sculpts order from chaos, that transforms simple hydrogen into the rich complexity of a universe filled with stars, planets, and potentially life. In a sense, we owe our existence to gravity. The atoms in your body were forged in stellar furnaces that gravity ignited and later dispersed in supernova explosions gravity triggered. The planet beneath your feet assembled from those atoms through gravity's patient accumulation. Every breath you take is held to Earth by gravity's embrace. The study of gravity continues to reveal new mysteries. From the discovery of dark matter and dark energy to the detection of gravitational waves, to the imaging of black hole shadows, our understanding of gravity keeps deepening. Yet fundamental questions remain. What is dark matter? What is dark energy? How can we reconcile general relativity with quantum mechanics? Some theoretical physicists have explored whether there might be extra dimensions of space curled up too small to see, or whether there could be a fifth fundamental force, though these ideas remain untested. Do the laws of gravity apply the same way everywhere in the universe and at all times? Each answer we find opens new questions, like peeling back the layers of an infinite onion. Gravity, which seems so familiar, so simple in our everyday experience, remains one of the great frontiers of physics. A mystery that beckons us ever deeper into understanding the fundamental nature of reality. As we draw toward the close of our journey through these 100 facts, allow yourself to feel the presence of gravity all around you. Feel how it presses you gently against your bed, how it grounds you to the planet beneath. This force that seems so ordinary, so unremarkable in daily life, is the invisible architect of the cosmos. It shapes galaxies, powers stars, creates the tides, and binds together everything from atoms to superclusters. It curves the fabric of space-time itself, warping the very dimensions through which we move. It connects you to every other piece of matter in the universe through invisible threads that extend infinitely in all directions. The atoms in your body were forged inside stars that gravity ignited billions of years ago. They were scattered across space when those stars collapsed under their own weight and exploded. Gravity gathered them into the cloud that became our solar system, compressed them into the planet beneath you, and now holds you in this moment, in this place, allowing you to exist. You are gravity's child, formed and shaped by this fundamental force. From the smallest flutter of a falling leaf to the grand spiral of galaxies across the void, gravity weaves the universe together in an endless dance of attraction and motion. Let your breathing slow even further. Let the weight of your body settle into stillness. Feel yourself held by gravity's gentle, constant pull, connected to the earth below and through the earth to everything else that exists. The moon overhead, the sun beyond, the stars scattered like diamonds across the night, all bound by the same force that holds you now. In this quiet moment, you are part of something vast and ancient, a universe shaped by gravity's patient, invisible hand. Rest now, held safely by the force that has guided the cosmos since the beginning of time. Let gravity do its work, pulling you softly into the quiet dark where thoughts dissolve like morning mist. Tomorrow awaits with new wonders to explore. But for now, simply drift, weightless in your mind while gravity cradles your body, ancient and eternal, forever pulling, forever connecting, forever shaping the universe around you. Sleep peacefully under the watch of gravity's gentle embrace. If you enjoyed this peaceful exploration of the cosmos, consider leaving a like, subscribing, or sharing a thought below. It helps others find their way to these calm discoveries, one soul at a time. Until we meet again beneath the stars, rest well. Good night.